Titration of a sodium carbonate and sodium bicarbonate mixture with hydrochloric acid. For this experiment, we start by making a solution using a mixture of sodium bicarbonate and sodium carbonate. And if you obtained this mixture from the decomposition of baking soda, then you may not be so certain that all your sodium bicarbonate fully converted to sodium carbonate until you confirm it using at least one method. For example, this titration, you need to assume that not all your sodium bicarbonate is fully converted. So you start by measuring a known mass of the mixture that you created from the decomposition of baking soda into a volumetric flask. Add small increments of water, swirling consistently until it's fully dissolved, and then you will add water until the mark without exceeding it, because you can't remove any water from it. Once you made your solution and it is homogenized, then you can proceed to do some calculations. One of the first things that may come up is, how many moles of sodium carbonate and sodium bicarbonate do you have in your solution? And the answer is, we can't calculate this because we don't know what is the proportion in the mixture of the sodium carbonate and sodium bicarbonate. And so if your task is, what is the number of moles? Just by making a solution, you can't determine it. And if the task is to determine the concentration, you still can't do it, because without knowing the moles of your solutes, determining concentration as molarity is impossible. So then we can proceed to our titration and maybe elucidate the composition of our mixture. Titration is a quantitative analytical technique in which we have a standard acid, in this case the 0.1 molar hydrochloric acid that we use to charge the burette with. And on the bottom we have an Erlenmeyer flask that has our mixture of sodium carbonate and sodium bicarbonate in it, dissolved in water with some phenolphthalein indicator. We're going to titrate or add small increments of our standard acid to this base mixture until the indicator changes color, which in the case of phenolphthalein is turning from a vivid magenta pink color to the very palest shade of pink you can achieve. At that point, we are going to assume that our titration reached its end point and all the sodium carbonate from the solution successfully converted to sodium bicarbonate. So as we perform our experiment, these are the measurements we need to collect. At first, we are going to have an exact volume for the solution that contains both the sodium carbonate and the sodium bicarbonate in it. And then we're going to record the first volume on the burette for the hydrochloric acid. After that, we titrate using the phenolphthalein indicator until the color turns the palest shade of pink, at which point we record the volume of the hydrochloric acid in the burette. The difference between these two volume measurements is going to be the volume of hydrochloric acid needed to titrate the sodium carbonate. Then we're going to add a few drops of the methyl red indicator, and our solution will turn yellow. We will then titrate until our solution becomes orange, and at the end, when we achieve the second color change, we are going to record the volume of the hydrochloric acid in the burette again. In the second titration, we will determine the number of moles of sodium bicarbonate that have been titrated with the hydrochloric acid. So let's get started. We start with 19.8 milliliters of a mixed solution, and we titrate this with 0.1 molar hydrochloric acid. Task 1 is to calculate the volume of hydrochloric acid consumed in this first stage. So we're going to say the volume of hydrochloric acid needed to titrate the sodium carbonate. 14.67 milliliters, which is the second volume measurement on the burette, minus 4.00 milliliters, which is the initial measurement on the burette, giving us a difference of 10.67 milliliters. This is the volume of hydrochloric acid consumed to titrate the sodium carbonate solution. We can use this volume to determine the moles of hydrochloric acid consumed. We start with the 10.67 milliliters. We convert from milliliters to liters. And then we say each 1 liter of solution would contain 0.1 moles of hydrochloric acid if our solution is 0.1 molar. The milliliters and liters will cancel, and we will have 0.001067 moles of hydrochloric acid consumed in the first titration. Using the moles of hydrochloric acid, we can determine the moles of sodium carbonate, starting with the 0.001067 moles of hydrochloric acid. We're going to use the mole ratio of the first titration reaction. Every 1 mole of hydrochloric acid consumed will consume 1 mole of the sodium carbonate. Canceling the moles of hydrochloric acid, we will have 0.001067 moles of sodium carbonate. Now we move on to the second titration. We add 2 drops of methyl red indicator and we titrate until it turns orange. Step 1, let's calculate the volume of hydrochloric acid we need to consume for the second titration, and we say volume of the hydrochloric acid consumed with the methyl red indicator equals to 31.42 milliliters. This is the volume after the titration with hydrochloric acid in the presence of the methyl red indicator, minus 14.67 milliliters, which is the volume that we had after the titration with the phenolphthalein indicator before we added the methyl red indicator. The difference between these two is 16.75 milliliters. Knowing the volume of the hydrochloric acid solution consumed by the titration, we can take multiple steps and calculate the moles of sodium bicarbonate that were consumed. We start with the volume of the hydrochloric acid solution, 16.75 milliliters. Convert this to liters by acknowledging that 1 milliliter is the same as 10 to the negative third liters. Then we use the concentration of the hydrochloric acid solution. 1 liter contains 0.1 moles of hydrochloric acid. And then we use the mole ratios from the chemical equation. Every 1 mole of hydrochloric acid consumed would consume 1 mole of sodium bicarbonate. And we stop here because after the milliliters, liters, and moles of hydrochloric acid cancel out, we will have 0.001675 moles of sodium bicarbonate and sodium bicarbonate. We know that with the hydrochloric acid titration using the phenolphthalein indicator, only the sodium carbonate will be titrated, because in the presence of phenolphthalein, the sodium bicarbonate solution does not change the color of the indicator. So the moles of the sodium carbonate are going to be the moles that we determined from the first titration, 0.01067 moles. And all of these moles that were titrated with hydrochloric acid in the presence of the phenolphthalein indicator have been converted to sodium bicarbonate. So we have for the number of moles of sodium bicarbonate, the 0.001067 moles that were coming from the sodium carbonate titration. And then we have an additional amount that is coming from the moles of sodium bicarbonate that were present in the initial mixture. These two combined will give us 0.001675 moles, which is what we found in the second titration. So the initial moles of sodium bicarbonate in the mixture are going to be the total moles, 0.001675 moles, minus the number of moles that we got from the titration of the sodium carbonate present in the mixture, 0.001067 moles. And the difference of these two will be 0.000608 moles of sodium bicarbonate. Now that we have the moles of sodium carbonate and the moles of sodium bicarbonate that were originally in our mixture, we can calculate the mole fraction of the two ingredients. To calculate the mole fraction of sodium carbonate, we're going to use the number of moles of sodium carbonate, the 0.001067 moles, and we're going to divide it by the total number of moles, 0.001675 moles. The result of this calculation is 0.637. If we were to convert it to percentages, it would be 63.7%. Then if we calculate the mole fraction of sodium bicarbonate, we could do it in two ways. We could take 1 and subtract the 0.637 from it, or we can take the number of moles of sodium bicarbonate, which is the 0.000608 moles of sodium bicarbonate, divided by the total number of moles, 0.001675 moles, which is 0.363. Notice that I am not adding any units to these numbers because the moles canceled out. These are unitless values, just like percentages would be. But if you add these two numbers, you will find that they add up to 1, just like if you considered both ingredients, the percentages of those two would add up to 100%. Could we use these moles to calculate the mass percent? Absolutely. So in step 1, we would take the moles of sodium carbonate, convert it to mass, and sodium bicarbonate moles, convert it to mass. We start with 0.001067 moles of sodium carbonate. Each 1 mole of sodium carbonate weighs 106 grams, giving us 0.113 grams of sodium carbonate. We can do the same thing with the moles of sodium bicarbonate, 0.000608 moles of sodium bicarbonate will be divided by 1 mole of sodium bicarbonate and multiplied by the 84 grams of sodium bicarbonate that is the molar mass. We have 0.051 grams of sodium bicarbonate. Calculating the mass percent of the individual ingredients in a mixture would require a very similar calculation to what we've done with the moles. We're going to say percent sodium carbonate equals to 0.113 grams of sodium carbonate divided by the sum of the masses for sodium carbonate and sodium bicarbonate, which is 0.164 grams of the mixture, times 100, because we're calculating a percent, it will give us 68.9%. The percent sodium bicarbonate will be 0.051 grams of sodium bicarbonate divided by 0.164 grams for the combined mixture times 100, giving us 31.1%. And the sum of these two percents will be exactly 100%. If you round it differently, it may come out as 99.9% or 100.1%. If it's really, really close to 100, you can consider it correctly done. Now, just because we are able to calculate the mass percent, it doesn't necessarily give us a lot of information. The most information that we have comes from the mole fraction calculations. If we successfully decompose the sodium bicarbonate to sodium carbonate, then the mole fraction of sodium carbonate should be 1, and the mole fraction of sodium bicarbonate should be 0. If those numbers are not close to the 1 and the 0, then we need to go back, take our mixture, put it on the hot plate, and heat it some more until the results of our titrations start indicating that all of our sodium bicarbonate has fully decomposed to sodium carbonate.